Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 26, 2026, just about 3 days ago. It demonstrates that a new framework called SMTL can reduce the average number of reasoning steps on the BrowseComp benchmark by about 71%, while actually improving performance over existing models like Miro Thinker. The paper is titled, Search More, Think Less, Rethinking Long-Horizon Agentic Search for Efficiency and Generalization. And as we'll see later, the shift from sequential to parallel processing has some really promising implications for inference costs. So Figure 1 illustrates this performance leap, breaking it down into efficiency and generalization. On the left, panel plots efficiency on BrowseComp. Notice how the green stars for SMTL form a new Pareto frontier, sitting significantly higher than competitors like Miro Thinker, which indicates better results with less computational effort. Moving to the right, panel B uses a radar chart to show generalization. The expanded blue area demonstrates that SMTL leads across diverse benchmarks like Gaia and XBench, as well as on qualitative metrics such as readability. Alright, moving from results to methodology. Figure 2 outlines the parallel agentic workflow that makes this efficiency possible. The process begins on the left, where the model takes a high-level task and runs a decomposition step, breaking it down into subtasks like task 1 through task 4. Then, the center section illustrates the parallel execution phase. Here, the agent doesn't just work linearly, it launches concurrent threads to gather evidence for different subtasks simultaneously. These threads converge at the sync node below to integrate information, which allows the refinement module on the right to update the plan dynamically before merging everything into a final answer. Well, to train an agent capable of such complex parallel planning, the authors developed a specialized data synthesis pipeline, detailed here in Figure 3. The process starts on the left in the blue panel with graph network construction, where the system parses raw documents from the task-graph corpus into chunks and extracts entities to build a structured knowledge graph. Next, the yellow panel shows subgraph extraction, which uses breadth-first search to isolate specific clusters of connected information, ensuring the data requires multi-hop reasoning. Finally, the green panel illustrates question generation and verification, where the system iteratively creates harder questions and filters them for consistency to produce the final deep search and deep research datasets. So, having established the data pipeline, Table 1 reports the main performance results across both deep search and deep research benchmarks. On the left side, under deep search, SMTL 300 achieves 48.6% on BrowseComp. This score clearly outperforms comparable open-source models like Miro Thinker version 1 at 41.2% and Tongyi Deep Research. Moving to the right block for Deep Research Bench, SMTL 100 secures an overall score of 45.9%, effectively balancing comprehensiveness and depth to surpass other 30 billion parameter agents. Okay, while Table 1 focused on scores, Table 2 breaks down the actual interaction costs on BrowseComp. Notice that Miro Thinker requires 206 steps to reach roughly 41% accuracy, strictly adhering to one tool call per step. In contrast, SMTL 100 surpasses that accuracy with just 60 steps. The secret lies in the average tool calls column, where SMTL averages about 3.5 calls per step, which confirms that efficiency comes from parallelizing evidence gathering rather than sequential thinking. To see this efficiency in action, Figure 5 visualizes a case study searching for a historical figure. On the left, SMTL immediately launches a parallel search, breaking the problem into 3 concurrent subtasks. This strategy allows it to localize the key entity, Queen Marie of Romania, by turn 8 and finish by turn 36. In contrast, the right side shows Miro Thinker following a sequential path, processing clues linearly stage by stage. Consequently, it only identifies the entity after 16 turns and drags the final answer out to turn 150. Wrapping up, 2 takeaways stand out. First, scalability in research agents relies as much on parallel search efficiency as it does on reasoning depth. Second, structured context management allows these agents to tackle long horizons without losing the plot. This approach proves that we can achieve state-of-the-art results while actually thinking less. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.